Welcome everyone again to another seminar. Good afternoon. So today we have the pleasure to have Professor Jamilla Teixeira here. Let me give you her bio. So Dr. Jamilla Teixeira is an assistant professor at the Department of Civil and Environmental Engineering, the University of Nebraska-Lincoln. She earned her bachelor's degree from the Federal University of Ceará in Fortaleza, Brazil, in 2004. After that, she earned her master's and PhD from the University of Nebraska-Lincoln. Before joining UNL, Professor Teixeira was a professor at the Federal University of Espírito Santo in Vitória, Brazil. Her research focuses on the characterization of infrastructure materials, including rheological, chemical, and physical laboratory experimentation, as well as computational modeling of composite materials based on microstructure, multi-scale models, viscoelasticity, and fracture mechanics. More than that, she is also an amazing person, and we're very happy to host you here. So welcome, Professor Jamilla Teixeira.
Did I even see there and
Share from the Zoom. Maybe that's it. Yeah. Oh, fine. Again,
all right, good afternoon. Hello.
Hello.
It's a Thank you so much for the opportunity. For me, it's a really pleasure to be in such a great center, Illinois Center of Transportation. As Brenda introduced it, I'm Jamilla Teixeira, originally from Brazil, but today I'm in Nebraska as an assistant professor. And I'm going to present some of the works that I've been doing in the past 8 years, I would say. Most of the works that I'm going to present, they were developed in Brazil when I was a professor there. I just joined UNL last year. And it's about the use of slag. And you see this great material, and we have lots of options to incorporate this material in pavement. Okay, so again, thank you so much. I divided this presentation in 6 topics. First, a brief introduction. The main theme of this seminar series is transportation and climate change, right? So I try to connect why slag, why this topic is correlated or linked with the main topic of this seminar series. Then I'm going to show what is slag. For me, it's very common knowledge. I know what is slag is, where it comes from, but for many of you, you maybe don't know how we can get this material. So I'm going to quickly show what is slag, where it comes from, what is the original material that generates slag. And then I'm going to show 3 case studies that I work at. One, it's about the use of slag to stabilize soils. And the second case, it's about a difference that I observed when different types of slags were mixed with asphalt binder, and the way they adhere to the binder differs depending on the type of slags, and there are some reasons because of that, and I'm going to show a little bit. And then, and then the last case, I do work with numerical modeling, so I had to show a little bit of modeling and how I use it in modeling to try to infer if I use slag, how does it change the cracking evolution, initiation and evolution, and final fracture of an asphalt concrete, and final remarks. So just to start, transportation and climate change. Probably you already heard in many presentations that there is a concern in many seminars, webinars, that we are talking about climate change. And there are many effects, and especially on transportation systems, we are seeing the effects of climate change with extreme events such as floods, droughts, hurricanes, wildfire. And the cause, it's because we are increasing the amount of CO2 emissions, the way we are using the materials, and we are building infrastructure, we may be harming the planet. So the planet's well-being and health are threatened. So we need to find ways to minimize the impacts of our activities. So there is the projection of a climate change impact future are not inevitable. What I'm saying is that we can do something right now so that we have a better future for our planet at the end. So talking about the main contributions for CO2 emission, transportation sector is responsible for 29% of the US greenhouse emissions, as you can see on this graph from EPA. And when we talk about transportation, we have contributions from aviation, shipping, pipelines, but most of the contributions comes from the roadway transportation, okay? And part of these impacts comes from the production of materials and roadway building and maintenance activities. So just for material production and transportation, road construction and maintenance, we can account for 5 to 25% of the total carbon emissions from transportations. So we need to find a way to try to reduce that number. That is our contributions as people that work with infrastructure materials. Maybe not as big as other contributions for other sectors, but we still have to make our contributions to try to reduce the CO2 emissions. Okay, so what are the alternatives to minimize the impacts of roadway material production? So there are many ways that we can think as engineers, as materials engineers, to contribute to less CO2. One way, the way that I like and I love to research is by recycling and reusing materials that we already have available. So why to extract new materials if there are local materials that we can use, right? This is one way. So we can minimize the extraction of natural resources and recycling and reuse what we already have available. Second, again, using local material, we reduce the transport distance of the material. So less fuel consumption, right? Okay. Okay, and this also contributes to the reduction of CO2. And again, okay, we can get local materials are locally available. We can mix, but it's not going to help if the interaction of this material is not good with conventional pavement materials. So we gotta also try to find a ways to design and optimize the use of those materials so we can have durable mixtures at the end, mixtures or pavement base layer materials. So this all helps the pavement sustainability. And that's where slag comes into play. When I think about slag, I can think, if I have a slag company, a slag supplier close to my construction, I can recycle and reuse that material. I can reduce the transport I can optimize the transport of materials. I can use slag in place of natural aggregates. I can minimize the extraction of natural resource. And because of some of the slag properties, I can enhance the performance of my mixture or soil. So I can address many of those things, or I can see the slag participating in a positive way in many of those things that can contribute to pavement sustainability. So let's go to slag then. So what is slag? Slag comes from steel, and steel, one of the most used materials in the world, okay? As the second most widely utilized material globally. Globally, production of steel goes to 1.8 billion tons. It's a lot of material that is out there. US, 85 million tons are produced every year. So we're talking about steel. But during the production of steel, we have the generation of this co-product, okay? This seems like an aggregate pile, doesn't it? This is a recent photo that I took in Nebraska in a slag supplier. This material, when it comes from the steel production, comes very hot, and then when it cools down, becomes like an aggregate. Okay. And then this is a great material, and I'm going to show you some of the properties of this material. And we can use it. And in fact, it has been used in many countries and continents. In US, roadways are using 49%, but you still have 15 to 16% that are just disposed on landfills. Okay, and even the roadway construction, it's used, but maybe we can have a better use on roadways. They are used, but just for local roadways or paving rural areas, but maybe we can use for a novel structures. So what are these slags? So you know slags comes from steel, it's a co-product. Let me show you that there are different types of slags. So, but before talking about slags, let me show you how steel is produced so you can understand where slag comes from. So to produce steel, we need some raw materials such as iron ore, limestone, and coal. Those materials goes to a pre-processing, and then they comes into this first furnace that is called blast furnace. This is to transform the raw material in molten iron. Okay, this is the first thing that we do to get to the steel. We produce molten iron. Then the molten iron, depending on the industry, they want to remove excess of sulfur because this improves the quality of steel. So the molten iron goes to a desulfurization process. And this furnace is called Canberra reactor. So we remove excess of sulfur from molten iron. And then the molten iron goes to another furnace. It can be basic oxygen furnace, or it could be electric arc furnace, depending on the steel company, to transform molten iron into steel. And then steel goes to its final process of refining and cutting, and then we have the final products. So let's see now slags. So in each of these process, we have different slags being generated. Okay, so from the blast furnace, we have the first type of slag, which is called blast furnace slag, or sometimes it's called iron slag, because it's during the production of molten iron. And about 200 to 300 kilograms per ton of molten iron are generated. From the Canberra reactor process, we have about 120 kilograms per ton of steel of this slag being generated. From the basic oxygen furnace, we have the BOF slag, and then from the electric arc furnace, we have the EAF slag. So it's really important to understand that in each of those parts of steelmaking process, we have different slags. Before, when people were not using slag as a pavement material, they were all blended together, very heterogeneous. So it's really important to separate the materials, like plastic. We gotta separate LDPE, HDPE, polypropylene, so we can have a better idea of the material characteristics, so we can better blend and optimize the materials. Same thing for slags. So we saw that there were different types of slags, and all of them, they possess good solidity, good abrasion resistance, high angle of friction, high strength. However, they differ in terms of chemical and thermodynamic characteristics. The slides are passing automatically. I don't know why, but that's okay. I will keep the pace as it's passing. So, it's good or too fast? It's good. Can I continue in this pace? All right. So you understand different types of slags, same mechanical properties more or less, but different chemical characteristics. And this is affecting the way the slags gonna interact with pavement materials. So for asphalt pavement, if I want to use this material for asphalt pavement, first I need to identify what type of slag, because I showed you 4 types, what type is better or it's appropriate in each layer, because each layer has its own properties requirements, control parameters. So I need to identify. If I want to use in base sub-base, what are the control parameters? Can I use for soil stabilization? If I want to use for the surface layer, how this slag is going to interact with binder, asphalt binder, or other aggregates, or the interlock, it's good or not. So depending on the layer, see, you move it. So we need to identify the use so we can select the better type for each layer. So to do that, what we did, we select those 3 slags here, which were the ones that were available in Brazil when I started to work with slags, and we did a preliminary characterization. Very simple characterization, common aggregate properties that state duties they do. So we checked book specific gravity, absorption, Los Angeles abrasion, sodium sulfate soundness, adhesion, and the expansion of this slag. So what we noticed was that BOF, blast oxygen furnace slag, it passed on the requirements for aggregates to be used to produce asphalt concrete. So we said, well, BOF can be a candidate for HMA application. The BF slag, we saw that for a simple boiling test, we didn't see a good adhesion of the BF slag with the binder. So it did not pass, and also had higher absorption. This could be a flag that, oh, if I decided to use BF, I need to add some additive to improve the bonding with this slag with binder. And I also have to be careful with the amount of binder that I need because there is a higher absorption of this material. It might increase the costs, right? And we can lose durability if the asphalt film thickness is not enough, right? And KR, same thing we observed in terms of absorption. When we started this research with KR in Brazil, one of the concerns from the company was with the KR slag. They had huge piles and no use. They were going to landfills. So we start to focus on the KR slag when we start research on the slag use. So we went a little bit deeper on the KR and we did a size distribution analysis. We saw, well, this material is well graded. Maybe it can act like a rock and we can stabilize soils like by mixing soil with aggregates or mechanical stabilization. But we also noticed from chemical analysis, X-ray fluorescence analysis, elemental composition, we saw the presence of silica, calcium, and iron, which are also common in cementitious materials such as Portland cement. And from X-ray diffractogram, we saw the presence of Portland, quartz, calcite, and ettringite. So these gave us insight of, this slag not only can be good for mechanical stabilization, but might give us some chemical stabilization because of those chemical components. So chemical stabilization induced by cation exchange and formation of hydration process, those were our initial thoughts. So we decided to move on for this study here about the use of clay soil stabilized with KR slag. So in this project, those 2 students worked on that project. The idea was, the hypothesis was, can we use KR slag as for chemical and mechanical stabilization? We had some reasons. Well, if this works, this can be a very sustainable material. We are minimizing the natural aggregate extraction. We don't need to blend with natural aggregates. And if this slag can be used in place of hydrated lime or Portland cement, we automatically reduce the use of materials that contributes a lot for CO2 emission. So we are reducing CO2 emissions. More than that, cement or hydrated lime, they are not cheap materials. If we can use slag that at that time has no cost, we had economical reasons. And besides that, this slag, it's a slag that does not expand, which is one of the concerns when we work with unbounded materials, is the expansion. So to evaluate that, we did some laboratory investigation and also we built some field sections. And I'm going to show just part of the results due to time limitations here. First, one thing that I want to point out, when we selected 2 soils, soil 1 was a poor soil, clay soil, that could not be used to build pavement layers, base or super base. It was a A76 soil, CBR very low, resilient modulus very low, we couldn't use. But when we add slag, first thing that we noticed was the reduction of plasticity index. And this reduction was observed for the two types of soil. Soil 2 was more like a sandy soil. So we observed that the clay soil, the reduction in plasticity index was higher than in the sand soil. So one thing that we start to hypothesize, there might be some cation exchange happening. And we are reducing the double diffusion layer that are present in clay soils. Clay minerals are interacting with cations from the KR slag. And that may be the reason that we are having this reduction in the plasticity index. We did some mechanical tests. I just put resilient modulus and CBR, and I highlighted the two cases here. The poor soil with 20% slag, and then the better quality soil mixed with 3% of Portland cement. This was the common solution locally in the state that I did this research. They were using this for sub-base layer. But our alternative was, instead of using a soil that is not available close, you have to go a little bit far to get this better quality soil, and you have to mix with 3% of cement. Why don't we use this poor soil but mix it with slag? Because we saw some similar mechanical performance. So we select those two soils and we build field sections. Brazil, this is the state that I work in. We built two field sections, 80 millimeter long by 4 millimeter wide sections. And those two field sections, they have the same asphalt layer, same base layer. The difference was the sub-base layer. One with better soil with 3% Portland cement, another one with clay soil with 20% KR. And then we did the sections, we placed it, this looks like a truck, this is a heavy vehicle simulator. So we place this heavy vehicle simulator on top of each section, and that is let me pass, otherwise I cannot talk. So this heavy vehicle simulator was placed on top of each section for a 3-month period until 1 million passes of this wheel load completed on the vehicle. So and we measure the deflection and the road depth periodically every 2 weeks. So we monitoring, and those two sections, they perform very similarly, and the deflections were very low and very much below the maximum limit established by the concessionary, and also the road depths were under the maximum limit. That was a result that for the concessionary that was funding this research, they said, wow, maybe this is a good solution for us to apply and to construct pavements. So they started using then the poor soil with slag to duplicate the highway. But we want to go further and see, what is happening? What KR is doing with this clay soil that is justifying this good result? So another student, he did some microscopic analysis, microstructure analysis, and chemical analysis. He quantified the cation exchange capacity of the KR, and he observed that the total cation exchange was 47 and was similar to values found for common binding agents such as Portland cement or hydrated lime. He also saw that the contribution of the cation Ca2+, it was more predominant, and this cation can exchange more easily with clay minerals and give the positive results of flocculation and agglomerations that we expect when we stabilize a soil with calcium-rich material. Also, we took this soil sample and we evaluated in the microscope after 4 days and after 28 days, what we observed when we mix it with KR, we observed the creation, the appearance of those fibrillar, those needle-shaped structures. And this is also observed when Portland cement has its hydration reaction occurring. And can give extra strength for the material, makes the microstructure more dense and increase the strength. So for us, this was an evidence that slag was helping the clay soil by cation exchanging, reducing the plasticity, creating agglomeration and flocculation, and also a strength gain because of the hydration of some of the chemical components. In another study, I showed you two other types of slag, BF and BOF. BF showed very poor adhesion to the binder. You can see on this image, it's very clear. Same amount of binder in a different type of slag, you see that good adhesion, right? Very empirical test, but give us this initial insight. When we took those slags and we used to produce asphalt concrete in a moisture damage test, when I replaced natural aggregates by BF slag, the TSR value, I don't know if some of you may be familiar with moisture damage test, was 54%, which is low. We expect at least 70%. When we replace natural aggregates by BOF, then the strength, the moisture damage resistance increased comparing with our reference mixture. This was expected because we knew this slag had a better adhesion. But you want to know why this slag is having a better adhesion than this one? They comes from the same industry. What is happening? Check that. We try to evaluate the binder aggregate adhesion through different perspectives. And binder and aggregates, they interact with each other, and the adhesion can happen because physical interactions, physical adhesion, can be due to thermodynamic interactions, thermodynamic adhesion, or can be through chemical interactions, chemical adhesion. So all those things can contribute to a good binder aggregate adhesion. So we need to, talking about balanced mix design, I try to use the same concept, try to balance chemical, thermodynamical, and physical properties of the slags to have a better adhesion. To evaluate the binder aggregate adhesion, what we did evaluate physical adhesions using AIMS and laser scanning microscopy. AIMS to check texture and angularity difference between those two slags. Laser scanning microscopy to check rugosity of the materials. Those things can contribute to the physical adhesion. Thermodynamics, we measure the surface free energy of those two slags to see if they were different. And we also check the wettability of the slag by the binder by measuring the contact angle. And we also use AFM to check the work of adhesion between the binder atoms and the slag atoms. So we could use FAM to check that. And finally, we check the chemical composition of those two slags by using X-ray fluorescence. So AIMS results I didn't plot here, but they were very similar. So the difference in angularity could not explain why one slag was better, adding better with binder than the other. From the surface measurements, we saw that the BF slag has a higher roughness than BOF, which could result in a better adhesion, but that was not what we observed. But the values were not too high. In comparing with that standard deviation, we can say that, well, this is not the reason why one slag is performing better than the other. Let's check surface free energy results. Total surface free energy, what I was expecting, me and my student, was that the BOF could have a much higher surface free energy. That could justify to us that BOF was better because of higher surface free energy. But again, the values were similar, but still comparable with limestone aggregates, which are the ones that better adheres to the binder, are not exit aggregates compared to granite aggregates. Talking about this surface angle, we saw that the BOF showed a little bit lower angle. We can relate that the lower the angle, it's better wettability, and the better wettability, the better adhesiveness. A little bit lower than BF, a better slag in terms of addition with BF, but it's still not so different to justify what we found. So later, then we took AFM and we took the tip of AFM and we dip into the asphalt binder. And then we approximate the tip to the slag substrate. And from this test, we can measure how the chemical components, the atoms from the binder, it's interacting with the atoms from the slag. So we have a graphic like this. As the needle approaches the aggregate, they don't have interactions from a far distance, but as get close, they start to have influence to each other until we have a good bonding between the atoms. And then when we comes back, they start to lose the force, the adhesion between them until they don't interact more with each other. So the way to quantify this work of adhesion is to calculate this graphic. This is the graphic that we obtained, many images, actually, not only one, but thousands of images from the BF, and for the BOF, we got this. The interaction between atoms continues for a much longer distance, and the area was higher. So we saw that this could be one of the potential reasons that BOF had a better adhesion than BF. And finally, we checked the chemical composition. ASBF is the BF slag, and this is the BOF slag. We also noticed that the BF slag, the iron slag, had a much higher silica content than the BF, lower iron components content than the BOF slag, more or less the same calcium oxide percentage. And we know from literature, silica aggregates, they are acid aggregates, they don't have a good adhesion with binder. This is what makes sense when we look at the BF slag amount of silica. Iron, many literature suggested that the higher the iron content, the better adhesion. It makes sense also from our observations. And calcium, they were the same, so this was not considered a variable. So the chemical evaluation help us to identify the potential reason why one slag worked better with binder than the other. But can I use blast furnace slag? Doesn't have a good adhesion. Is there a way to improve? One way to improve is by adding some additives, such as hydrated lime. Everybody knows to minimize moisture damage, you can add hydrated lime. So we added 2% of hydrated lime from the original mixture that we replaced natural aggregates by 25% of BF. When we added hydrated lime, then the tensile strength ratio increased, which was the result that we were expecting. We also tried to use a powder from the steel industry that was rich on iron. And this powder seems also a good alternative to improve moisture damage resistance. And also we replaced we added BF slag to see if that could also enhance. We put a little bit of enhancement by just adding BF slag on the surface. This study also tried to evaluate the same powders, how they could affect the fracture resistance of the mixtures. So we did SCB tests before and after being conditioned. And what we observed was that when we just evaluate SCB test without submitting to moisture condition, all fillers, they kind of behave the same. So we didn't have the effect of the chemistry of fillers acting to improve the fracture resistance. But when we subjected the mixtures to moisture damage, then we start to have the interactions of the chemical components of the filler with the aggregates and binder, and then the materials behave totally different. If we just look the maximum force, they have the same, almost the same ranking order of the TSR values. But when we look into the fracture energy and the flexibility index, then you can see really that there is a difference depending on the filler that you add, the chemical composition of the filler, and by inducing moisture damage, you can really differentiate the dizziness and the contribution of each filler on the adhesion resistance, and as a consequence, the resistance to fracture. Hydrated lime has the lowest flexibility index, and we attribute that because hydrated lime enhances the rigidity, the mixture becomes more stiff, and then in that way the cracks propagate faster when we use hydrated lime. The EP powder was the one that for us, it didn't increase too much the stiffness, but it still improved the adhesion. So that in that way we improve the flexibility index. Finally, in this last study, we tried to evaluate what if slag is used as a filler in a conventional asphalt mixture. All right, so we took two, it's going, stay there. We took two samples and I know, going really fast, I don't know why.
Pushing her.
See? Well, can we just remove this? Because I need to stop and explain.
Something on the keyboard, maybe press the.
Is there something on the keyboard?
Let's get a flavor.
Let's see.
But that's good like this. Maybe she doesn't put that finish.
So I'm not.
Well, and also it increases.
Okay,
It
this
looks
is
like
the last study, okay? It's too many information, right? But the last one. So we took two asphalt mixtures, one we add hydrated lime and one we add slag powder. Come on.
That's good. Like, you do get
This
it.
subject,
That's good.
the trivial to explain in 1 minute. I need time.
If you can exit the presentation.
Yeah, exit.
Yes, right.
Oh, yeah.
Or just the numerical model and then cracking propagation, right? Let's see.
Leave it.
Just leave it, maybe down. Yeah, like that.
We found the
In this
presentation
mode.
mode.
Yeah.
Okay. Okay, so in this study, we try to use numerical modeling to infer how the addition of slag were changing some fracture parameters, and each fracture parameter can be associated with how fast the damage is propagating, and also when the crack is being initiated. So there are many insights that we can get. So this student, she took two samples. The only difference was the types of filler. One is slag, one hydrated lime. She did some frequency sweep tests where we could get master curves from dynamic models as a function of frequency. We converted and to the time domain, and we obtained the Prony series. That was important for the modeling. Then we also did SCB tests to get fracture parameters by doing a calibration process. And once we got Prony series, linear viscoelastic properties, and fracture parameters from the model that we use, we could then simulate another test that was used as an IDT test for validation. So let's see how the difference that we got. Before showing the result, let me just talk briefly about the numerical model that we use. We use a micromechanical model based on fracture mechanics. where we can evaluate the crack initiation and propagation explicitly. It's not an indirect way, it's a direct way to see when a crack starts and when crack starts to propagate. For that, we can use what we call cohesive zone models, and there are many cohesive zone models published, available in the literature. We used it in this study, the nonlinear viscoelastic cohesive zone model, which is defined, the mathematical description is this big equation. We have the convolution integral here, embedded in the model. That's why it's a viscoelastic model. It's nonlinear because if you see the relationship between the traction and the displacement, you have a nonlinear curve. And we have several parameters. But one of the parameters is this alpha function. And alpha is an internal state variable that is going to count how the crack is going to propagate, how fast, okay? And in this particular study, we use a phenomenological damage law where the alpha function as a function derivative in time, can be defined by this power law. So we have A and M as damage parameters. In this study, you can see later on this paper that each of the model parameters, they affect the way that the force displacement curve respond, the response of the material. The higher the delta, it seems like the material becomes more ductile. We increase we reduce the maximum peak load and the fracture energy increase. The higher the sigma F is this term here, is the stress initiation criteria. The higher the sigma F, meaning that the longer it's going to take to create a damage zone. This was very common observed in more brittle materials. And then the lower sigma F is observed in materials that are less brittle. The higher the A, you can see from this relation, the higher the A, the higher the damage propagation rate. So you can relate it with that. Same thing, the lower the M, the faster the rate of propagation. So when we did the calibration, so we create a finite element mesh, mimic exactly the same dimensions as the sample that you do in the lab. And then we play with those parameters, A, M, sigma F, and delta, until the results from what we obtain in the experiment match with the simulation. This is what we call calibration, okay? It's not a prediction, it's just a calibration. We try to match the curves. And we can get nice videos like this. We can observe as the sample is loaded, we have compressive stress on the top, we have tensile stress developed at the crack tip until at certain level of stress, the stress is too high, then the crack starts to propagate. And that's what you're going to observe here. The tensile stress is getting higher, until there is a point that the sample does not sustain anymore, and the crack starts to propagate. So we did this calibration for the two samples. And from the difference of the parameters, we could get three things here. Sigma F was higher for the mixtures with hydrated lime, which is this one. The higher sigma F, it's related to more brittle is the material. Makes sense for us from the SCP test that we did with hydrated lime, that hydrated lime presents more brittle fracture behavior, a very steep post-peak decay curve. Also, when the M value increases for the mixture with steel slag, meaning that the damage occurs more slowly. So slag was able to reduce the rate of damage propagation on the sample. And also the sample with slag had a higher delta value, meaning that the mixtures were more ductile. So these were things that we could observe from the SCP test. Now using those same parameters, we simulated the IDT test using the same parameters from SCP and frequent sweep test. So we could get A good prediction, now we can call this a prediction because we didn't calibrate. We used parameters from STB and from frequency sweep test. And we got the same, the good correlation on the curves. The initial slope, it was an indicator for us that the linear viscoelastic progress were satisfactory, well obtained. We didn't get a good match after peak. And for us, that could be an indication of IDT, we have mixed mode cracking being developed, not only mode 1. And in this simulation, we didn't consider mode 2 cracks. That could be a reason for not having a good match on post-peak curve. But still, it was a good correlation for us, and the model was able to predict the material response to cracking. And again, this is just nice videos to show. This is the mixture with hydrated lime. Let me show you the final results. So the same graphic that I showed you, we can go back to the contour plots and analyze how the concept zones are being inserted and how the damage is propagating until we have the final sample failure. And this is the mixture with slag. You can see that you have a lot of cohesive zones being inserted, which gives compliance to the neutral damage dissipation through because of viscoelasticity, but crack doesn't open. So that shows that this mixture is more resistant to crack. And final remarks now. You saw here, so some results confirms that slag can be an option. It's important to identify which type of slag you are working with to identify the better use. It's important to understand physical, chemical, and mineralogical characteristics of each slag, so you can better define the appropriate use. KR slag was very nice, a promised alternative for soil stabilization due to cation exchange capacity and also some hydration products that were observed. BOF and BF could be alternative for asphalt. We observed a better bonding of BOF slag with binder and could be attributed to the presence of ferrule components and calcium oxide, and also because of its thermodynamical properties. But BF is still viable if we add some additional modifiers. Finally, our team, most of this work was done in Brazil, as I said, but the slag research is going to continue in Nebraska. We already identified a slag supplier that we're going to work with. And not only slag, we are interested to research different types of alternative materials to contribute to pavement sustainability, such as waste plastics, wrap, vegetable oils, recycled concrete aggregates. Those are all alternatives that we are currently researching. And finally, just acknowledge my former university office in Brazil, my colleague Patricio Pires, who was my partner on all those projects from Brazil. This is my group of students from Brazil. Not all students are in this picture, but I highlighted one of the days that we cleaned the lab. You should clean the lab.
Yes.
Okay, it's really important. And this is my group in Nebraska now. So I have 2 PhD students, 1 master's students, 2 undergraduates so far. And finally, just a motivation. I know many of you are here from sometimes from different countries, missing your home, but continue to dream big, then you can accomplish your goals. This is my Annie card when I started as a student in Nebraska. Student 2004, faculty 2022. Okay, thank you.
Okay, thank you, Professor, for the nice presentation. Yes, Angeli, let's start.
Thank you for the nice work, Professor Teixeira. I have a question regarding your model. So it looks like it's a continua, right? It's a continuum and also homogeneous, but I wanted to understand if you can explain the growth or how the cohesive model, because it's bubbling at a different rate over time. How does that work when you have your model is inherently homogeneous and also is a continuum model?
Because I consider a homogeneous, that's what you were asking?
Well, the growth of the contour is no longer symmetric in any direction. So I'm unclear why that is because of the cohesive zone model.
Right, that's because when we start insert at the beginning, it's homogeneous, right? But because of the insertion of cohesive zones, then the distribution of stress pattern changes. But the model accounts the way that cohesive zones are inserted depending on the stress level in each point. So automatically it's inserting cohesive zones. I don't insert any cohesive zones a priori. It depends on the stress criteria. And this changes the stress pattern. If I predefine it, I could get maybe a homogeneous, but that's not what happened in reality. Once you have cracks develop, you don't have a homogeneous stress distribution. That's what we expected. And that's the reason, because cohesive zones are inserted as needed, depending on the stress level. Thank you for your question, Angelique.
And if I may have, sir, a super more general question. So it's nice that you were able to compare the different stages of the furnacing and creation process. Is it realistic that the stockpiles are separated? And if it's not, what do you do? Because you showed that there's an importance, like when you pick it from this station, this station.
Right. No, it's a good point. This is I always bring that slide at the beginning, more to give the industry the awareness of the importance of separating. In Brazil, it's a reality. They separate. They have piles of POF, they have piles of KR, but some steel industries, they just blend it together on purpose. So that's why I try to show this presentation. Whenever I talk about slag, I start showing the importance of separating the materials. Same thing for other, as I said, plastic. We want to use plastic, but first we need to separate to identify the contribution or difference among each material.
Okay, do we have any more questions? Okay. Okay, so we are at 2:50, right on time. So thank you, Professor, for that.